Hello everyone. In this talk, we will have a brief discussion on engineering integrations, potential applications, and outlooks of Li-ion batteries. This speech video is prepared by Dr. Xian-Ching Chung. Dr. Xian-Ching Chung appreciates that the committee invites him to give a talk at this conference. Especially, Professor Ming-Fa Lin for inspiring him to study this topic. Super Double Power Technology Company, Limited, SDP, is a research and development company, established in 2010. At early stages, SDP has developed lithium-ion batteries for electric vehicles. Currently, SDP focuses on the development and application of lithium-ion battery energy storage systems. The company maintains a close relationship with industry, government, education, and research institute in developing energy storage systems. The product line ranges from small portable energy storage suitcases to medium-sized energy storage systems. SDP provides complete solutions for off-grid solar energy storage systems, solving power supply problems in areas without power grids such as outlying islands and high mountains. Actual system operation case: the off-grid solar energy storage system of Peiyun Lodge in Mount Jade, Taiwan, the highest lodge in Taiwan, has been in operation for more than 6 years and is still in operation. SDP maintains a close relationship with industry, government, education, and research institute in developing energy storage systems. Some partners are listed below. Owing to the rapid development of renewable energy and the popularity of electric vehicles, lithium-ion, Li-ion, batteries are intensively used, causing more research on safety standards, repurposing batteries, failure analysis, as well as next-generation energy materials, such as graphene and other two-dimensional materials. In this talk, the engineering integrations on combining Li-ion battery cells to an energy storage system, ESS, are introduced. The battery management system, BMS, plays an important role in using the battery system efficiently and safely. The energy management system, EMS, can well integrate the ESS and other systems, such as renewable power sources and loads. Current potential applications for power and stationary application on various size scales are demonstrated. The outlooks on the future of Li-ion batteries are given at last. In this talk, the Neural Text-to-Speech, NTTS, service, using advanced deep learning technologies, is applied to support this talk. This talk will be given in the following structure. In the first section, a brief description of Li-ion batteries is given. In the second section, we talk about engineering integrations, including battery management systems, BMSs, and energy management systems, EMSs. In the third section, the power and stationary applications in various scales are demonstrated. In the last section, the outlooks on the future of Li-ion batteries are discussed. The widely use of lithium-ion, Li-ion, batteries in various fields, from 3C to grid-scale ESS, has revolutionized our way of life. The 2019 Nobel Prize in Chemistry has been awarded to John B. Goodenough, M. Stanley Whittingham, and Akira Yoshino for their contributions in developing Li-ion batteries. In this section, we will establish basic knowledge on Li-ion batteries and how to from materials to battery cells. Whittingham and colleagues at Exxon noticed that metal chalcogenides, MX2, possess a layered structure and available space to store Li-ions. They demonstrated that titanium disulfide, TiS2, can chemically intercalate Li-ions in its full stoichiometric range, showing minimized lattice expansion. In 1973 and 1974, Whittingham applied TiS2 as the cathode for Li-ion batteries and eventually exhibited a 2.5V battery cell in 1976. However, the formation of lithium dendrites, leading to short-circuiting, limits the application of Li-ion batteries. Later, Goodenough and colleagues had adopted oxide cathodes based on the understanding. In 1979–1980, Goodenough et al. Demonstrated that a lithium cobalt oxide, Li-2, can reversibly release and absorb Li-ions at potentials larger than 4.0 V, compared to Li+/Li, and enabled a 4.0 V rechargeable battery as coupled with the anode of lithium metal. In 1985 at Asahi Kosei Corporation, Akira Yoshino assembled a full rechargeable battery including the petroleum coke anode with Goodenough's Li-2 cathode. This battery was later commercialized by Sony in 1991 with a gravimetric energy capacity of 80 Wh/kg and volumetric energy capacity of 200 Wh/L. A modern Li-ion battery consists of two types of electrodes, typically lithium cobalt oxide, Li-2, as the cathode material, positive electrode, and graphite, C6, as the anode material, negative electrode. To avoid short circuit, they are separated by a separator with a porous structure immersed in a non-aqueous liquid electrolyte using LiP6 in a mixture of ethylene carbonate, EC, C3H4O3, and at least one linear carbonate, for example, diethyl carbonate, DEC, C5H10O3, dimethyl carbonate, DMC, C3H6O3, ethyl methyl carbonate, EMC, C4H8O3, with many other additives. Outside the Li-ion batteries, electrons are released from the anode, negative electrode, to the external circuit during discharging, powering the load as we thought. Inside the Li-ion batteries, the moving of Li-ions follows the shuttling process, or rocking chair concept. While discharging, Li-ions move to the Cu2 host structure. While charging, these Li-ions reversely move from the Li-Cu2 lattice structure to the side of the anode and form lithiated graphite, Lic6. The mainstream Li-ion batteries are commonly named by their active materials as shown in the red box. It can be cathode materials, i.e., positive materials, such as lithium cobalt oxide, LCO, lithium manganese oxide, LMO, lithium iron phosphate, LFP, lithium nickel cobalt manganese oxide, NCM or NMC, and lithium nickel cobalt aluminum oxide, NCA. Some are named by their anode materials, i.e., negative materials, such as lithium titanium oxide, LTO. There are several typical types of Li-ion batteries used in the industry. LCO and LMO-based batteries with medium energy capacities and high nominal voltages, 3.6–3.7 volt, are usually used in portable devices, such as smartphones and laptops. NCM and NCA-based batteries with high energy capacities and high nominal voltages, 3.6–3.7 volt, are usually used in power applications, such as electric vehicles. LFP-based batteries with low energy capacities, medium nominal voltages, 3.2 volt, and high safety features are usually used in large-scale power and stationary application, such as electric buses and grid-scale energy storage systems. LTO-based batteries with low energy capacities, low nominal voltages, 2.4 volt, and high safety features are usually used in power applications, such as electric vehicles and UPS. Li-ion batteries are composed of anode and cathode materials, electrolytes, separators, and other additives. However, it's not an easy task to produce batteries. From materials to batteries, there are many steps. As shown in the figure, the production flow chart contains mixing, coating, roller press, slitting, cutting, drying, pouch assembly, filling, formation, aging, cell assembly grading, quality assurance, and warehouse. According to the appearances, There are three types of battery cells, i.e., cylindrical cells, pouch cells, and prismatic cells. Each type of battery cell has its feature. The cylindrical battery cells are the most widely used. The pouch battery cells have the feature of being lightweight. The prismatic battery cells demonstrate high energy density. For example, the batteries used in Tesla EVs are 18,650 and 21,700 cylindrical battery cells. Li-ion batteries are one of the most widely used secondary battery systems in the world. Compared to other rechargeable batteries, for example, nickel-cadmium, nickel metal hydride, and lead-acid batteries, Li-ion batteries are featured with higher operating voltages, higher energy density, low self-discharging, and lower maintenance requirements. In this section, how to combine and control a set of Li-ion battery cells is described. To let many battery cells work together as a big battery, making an energy storage system, a battery management system is required. To make the energy storage system work with other systems, such as solar panels, converters, and inverters, the energy management system plays an important role. SDP provides solutions for off-grid solar energy storage systems. Our responsibility is to let the battery cells work together safely and efficiently. An extremely simple charge-discharge strategy for a single battery cell. It's simple to use a single battery cell as a power source. In the charge process, a charger is used with a charge voltage equal to or a little lower than the maximum charge voltage of the battery cell, V-cell sage cut. In the discharge process, a relay is used to cut the power off when the voltage of the battery cell is equal to or a little above the cut-off discharge voltage of the battery cell, V-cell discut. With these appropriate charge-discharge processes, we can easily use the battery cell, just as we use the cell phone every day. The above strategy on charge-discharge processes can be treated as a very simple BMS. Problems of the extremely simple charge-discharge strategy for multi-battery cells. Many people might think that the above simple BMS can be used for all battery systems with multi-cells. For example, a battery system is built by two battery cells in a series connection. In the charge process, a charger is used with a charge voltage equal to or a little lower than the maximum charge total voltage of the battery cells in series 5-tot sage cut, i.e., V-tot sage cut equals 2 V-cell sage cut. In the discharge process, a relay is used to cut the power off when the voltage of the battery cell is equal to or a little above the cut-off discharge total voltage of the battery cells in series 5-tot discut, i.e., V-tot discut equals 2 volts cell discut. These charge-discharge processes seem reasonable and easy to predict. We just double the upper and lower cutoff voltages, and everything will be okay. Indeed, the battery system actually can work under such brutal BMS, but only for a short time. The user will encounter serious problems in the battery system, i.e., overcharge and over-discharge. These problems result in the reduction of capacity and battery life, and even more dangerous fire and explosion, thermal runaway. Model battery system. The true story is much different when there is more than one battery cell. Because it is very hard to obtain battery cells with perfect charge-discharge characteristics, and then use them to build a dream battery system. To show the real case, a model battery system with 9 battery cells is given as an example as shown in Figure A. If we want to build a battery system with a triple voltage of the single cell and a triple capacity of the single cell, we should use a series connection of 3 cells, 3S, to triple the voltage and a parallel connection of 3 cells, 3P, to triple the capacity. NSNP indicates N battery cells in a series parallel connection. The general 3S3P configuration is shown in figure B. The cells are connected in parallel first to enlarge the capacity, and then connected in series to enlarge the voltage. The voltage of the cell is denoted by Vmn, and the voltages of the cells in the ITH series, parallel, connection are Vin, Vmi. For example, the voltages of the cells in the first series connection are V11, V12, V13. The voltages of the cells in the first parallel connection are V11, V21, V31. The cell voltages in the first, second, third parallel connection are detected by voltmeters VD1, VD2, and VD3, respectively. We will find that VD1 equals V11 equals V21 equals V31, VD2 equals V12 equals V22 equals V32, VD3 equals V13 equals V23 equals V33 due to rapidly dynamic balance among the parallel battery cells. Since the real battery system is built by the real battery cells with slightly different charge-discharge characteristics, the overcharge-over-discharge problems will happen if we use the system total voltage V total as the only reference. In the charge process, although the total voltage of the battery system is under the maximum total charge voltage, V total less than V total sage cut, one or some battery cells might exceed the cell charge cutoff voltage, in other words Vmn larger than V cell sage cut. For example, in the battery system with 3S3P configuration, as shown in figure B, the total voltage of the battery system, V total equals 2.9 V cell sage cut, is under the maximum total charge cutoff voltage, V total sage cut equals 3 V cell sage cut, but VD1 equals 0.8 volts cell sage cut, VD2 equals 1.2 volts cell sage cut, and VD3 equals 0.9 volts cell sage cut, indicating that the cell voltages V12, V22, and V32 are over the cell charge cutoff voltage V cell sage cut. In the discharge process, although the total voltage of the battery system is above the minimum total discharge voltage, V total larger than V total dis cut, one or some battery cells might come under the cell discharge cutoff voltage, in other words Vmn less than V cell dis cut. For example, as shown in figure B, the total voltage of the battery system, V total equals 3.1 V cell dis cut, is above the minimum total discharge voltage, V total equals 3 V cell sage cut, but VD1 equals 1.2 V cell sage cut, VD2 equals 0.8 V cell sage cut, and VD3 equals 1.1 V cell sage cut, indicating that the cell voltages V12, V22, and V32 are below the cell discharge cutoff voltage V cell dis cut. In these situations, we don't encounter the explicit overcharge-discharge event of the battery system, but the implicit overcharge-over-discharge event of the cell happens. The cell overcharge-over-discharge problems result in the reduction of capacity of the system and battery life, and even more dangerous fire and explosion, thermal runaway. These examples show that the naive battery management strategy based on simply enlarging the total charge-discharge voltage limitations is not suitable. Let's see a real case of the overvoltage of a battery system. The voltage variations of the real battery system in the Super Double Power Technology Company, STP, during charging are shown in the figure. This data is obtained from a lithium iron phosphate battery system, LFP battery system, with 16S5P configuration, using the Green Ice 50 LFP battery cells produced by Changhong Energy Technology Company. Since the system has been used for more than 1 year, the difference among charge-discharge characteristics of battery cells becomes larger, and is suitable for demonstrating the overcharge situation. The difference among charge-discharge characteristics of battery cells can be observed directly from the voltage difference between maximum and minimum cell voltages delta V as shown in figure C. When the system is near full charge state, delta V gradually increases from 30 to 187 millivolts, indicating that the voltages in various parallel connections gradually deviate and reaching the maximum deviation at delta V equals 187 millivolts. The highest voltage is 3.580 V pointed by the upper circle as shown in figure B. The lowest voltage is 3.393 V pointed by the lower circle in figure B. If V cell H cut is set at 3.5 V, there are 8 voltages above V cell H cut, indicating that overcharge event of the cell happens. However, the total voltage of the system V total equals 55.880 V remains lower than the V total H cut equals 16 V cell H cut equals 56 V as shown in figure A. Functionalities of the battery management system. To use the battery safely, a well-designed battery management system, BMS, is required. A BMS is an electronic system that manages a battery cell pack module system, such as protecting the battery from operating outside its safe operating area, monitoring its state, calculating secondary data, reporting that data, controlling its environment, and balancing it. Some functionalities of BMS are stated briefly below. Physical and electric quantities detection functions. The basic physical and electric quantities are measured, such as voltage, current, temperature, and pressure. Calculation functions. With the measured basic physical and electric quantities, further quantities can be simply obtained by comparators, subtractors, multipliers, integrators, and even more complex model calculations. Protection functions. When one or more measured basic physical and electric quantities reach the critical values, the BMS should take action to maintain safety and protect the battery. Alert functions. When the system encounters any of the protection conditions, the alert functions should be triggered to inform the administrator or user. Several inform routes are listed. Physical control functions. When the system encounters serious protection conditions, the charge/discharge processes can be terminated by relays. Communication functions. The BMS can provide the signal to other devices or the control center by various types of communication ports and/or protocols. Memory functions. The counters in the BMS can be used to record the number of some key events for evaluating the system status as the database is not available. Database functions. The database has the ability to record numerous data, which can give detailed operation status. Energy-saving functions. The BMS itself is an energy-consuming device. How to control its energy consumption is a problem. Various operation modes are suggested. Balance functions. Some BMS can balance the voltages in various parallel connections. Let's look at a real case BMS. In building an LFP battery system with 16S5P configuration, SDP chose to use a BMS providing measurements on 16 voltages in parallel connections, 4 temperatures, and 1 current. The BMS architecture is shown in the figure. The 16 voltages in parallel connection in the battery module are measured by 17 voltage detection points. The temperature sensors contact the surface of battery cells. The charge-discharge current is detected by the bidirectional Hall current sensor, providing safer no-contact sensing. The battery system can be charged by the charger. The charge current passes through the charge relay, R1, the diode, D1, and the fuse. If something wrong during charge, the charge relay will be turned off immediately by the BMS. The D1 diode guarantees that the current cannot feed back to the charger, avoiding damage to the charger by the feedback current. On the other hand, the battery system still can discharge to the load. The discharge current passes through the discharge relay, R2, the diode, D2, and the fuse. If something wrong during discharge, the discharge relay will be turned off immediately by the BMS. The D2 diode guarantees that the current cannot be feedback from the load. The fuse is used on the main power line as a passive overcurrent protection device. It is backup protection when charge and/or discharge relays do not work normally. The auxiliary power of the BMS is obtained from the DC-DC step-down converter, which converts the high-voltage power to the low-voltage auxiliary power. The main power switch is used to control the power on-off of the whole battery. When the main power switch is off, there is no auxiliary power passing through the BMS, and the charge and discharge relays are off. The BMS is under shutdown mode, indicating almost zero power consumption. Meanwhile, there is no current in and out through the battery system. When the main power switch is on, the auxiliary power passes through the BMS, and the charge-discharge relays are turned on and monitored by the BMS. This is the normal mode and the current can in and out through the battery system. The BMS provides bidirectional serial communication RS485 to the touch panel monitor. Some parameters can be set from the user interface of the touch panel monitor. The detecting and calculating data are sent to the local and/or remote database by CAN bus. Software for monitoring the battery system. Software for monitoring the battery system plays an important role in displaying the crucial data from the BMS. The remote dashboard of the BMS developed by SDP is shown in the figure. In the panel of basic information, some important physical and electric quantities, as well as the alert messages, are displayed, such as total voltage, current, power, max cell voltage, min cell voltage, the voltage difference between max and min cell voltages, max temperature, state of charge, SOC, system current state, and recent state change. Some data variations are also been shown, such as total voltage, cell voltages, delta V, current, power, temperature, and SOC. Let's see a real case for showing the power of BMS. With the well-designed BMS, the over-voltage condition during charge has been controlled and the battery system works in a safe region. When the highest cell voltage is larger than the over-cell voltage protection value, OCVP, it is 3.600 volt. In this case, the charge relay is turned off by the BMS and the highest cell voltage won't over the OCVP value in the figure. The OCVP will continue until the highest cell voltage gradually down to the release point of OCVP, 3.400 volt in this case. After the release point of OCVP, the charge relay will turn on and the battery system is ready for charge. If the charger provides current after OCVP release immediately, the cell voltages will rapidly increase to the OCVP value, and then the OCVP starts to function again. Energy Management System and Software. An energy management system, EMS, provides hardware and software to monitor, control, and optimize the energy systems. Also, EMSs can be used in various scales of systems, such as home energy management, automated control in buildings, and microgrids. In early 1990, it was common to find EMSs being delivered based on proprietary hardware and operating systems. EMS suppliers, such as Harris Controls, now GE, Spike, Control Data Corporation, Siemens, Hitachi, and Toshiba, manufactured their proprietary hardware. For EMS suppliers that did not manufacture their hardware, they often relied on products developed by Digital Equipment, Gould Electronics, and Modcomp. When proprietary systems became uneconomical, EMS suppliers began to deliver solutions based on standard industry hardware, such as those from Digital Equipment, later Compaq, later HP, IBM, and Sun. The common operating system then was either DEC Open VMS or Unix. By 2004, various EMS suppliers including ABB, Alstom, and OC had begun to offer Windows-based solutions. By 2006, customers had a choice of Unix, Linux, or Windows-based systems. Some suppliers including ETAP, NARI, PSICNI, and Siemens continue to offer Unix-based solutions. It is now common for suppliers to integrate Unix-based solutions on either the Sun Solaris or IBM platform. Recently, owing to the development and popularity of Linux-based systems, open-source software, and cloud technology, EMS suppliers start to extend their services to the cloud, developing the cloud-native open-source EMS on the Linux-based system. Energy management software, EMSW, plays an important role in the EMS, providing utility bill tracking, real-time metering, building HVAC and lighting control systems, building simulation and modeling, carbon and sustainability reporting, information technology, IT, equipment management, demand response, and/or energy audits. For buildings or communities, EMSWs often provide tools for reducing energy costs and consumption. EMSWs collect energy data and uses it for three main purposes, i.e., reporting, monitoring, and engagement. Reporting may include verification of energy data, benchmarking, and setting high-level energy usage reduction targets. Monitoring may include trend analysis and tracking energy consumption to identify cost-saving opportunities. Engagement may include automated and/or manual real-time responses, or the initiation of a dialogue between occupants and building managers to promote energy conservation. One engagement method that has recently gained popularity is the real-time energy consumption display available in Internet applications or an on-site energy dashboard. Let's see a real case of the energy management system. The off-grid solar energy system developed by SDP includes 4 parts, including 1. The photovoltaic, PV, panels generating the energy, 2. The ESS storing the energy, 3. The load indicating the energy consumption, and 4. The diesel generators providing the backup energy. The basic working strategy of the off-grid solar energy system is described below. The PV panels generate energy for the load and/or ESS. When the power of PV is more than the power consumed by the load, the rest energy will be stored in the ESS. When the power of PV is less than the power consumed by the load, insufficient energy will be supplied by the ESS. If the ESS is out of energy, the diesel generators will take over the supply work. The EMS developed by SDP can control the energy input of PV, the energy input-output of the ESS, the energy output to the load, and the backup power from the diesel generators. The EMS can work with default parameters to ensure the functionality of the basic working strategy. Also, the parameters and sensors in the EMS can be adjusted to fit some special cases. For example, we provide part of the EMS to Industrial Technology Research Institute, ITRI, Taiwan, which has an idea to build an off-grid solar energy system. The EMS parameters will dynamically be changed according to the weather database in Central Weather Bureau, Taiwan. Solar energy is expected to be largely used based on the predicted weather conditions. Let's see a real case of the energy management software. SDP develops the EMSW based on the Linux operating system, an open-source Unix-like operating system, as shown in the figure. The EMSW monitors the energy input of PV, the operation status of the ESS, and the energy output to the load. In the energy generation part, the power, voltage, and current of PV panels are monitored. In the energy consumption part, the power, voltage, and current of AC load are monitored. In the operation status of the ESS, the total voltage, current, maximum minimum cell voltages, and SOC are monitored. Their recent variations of important parameters are displayed for users to realize the energy generation time as well as for users to analyze their energy usage conditions. For example, as shown in Figure B, the PV panels began to generate energy at 6 o'clock, and the power gradually grew up to the highest power about 12 o'clock to 13 o'clock, and then gradually decreased to 0 at 18:30. The zigzag of the curve is due to clouds covering the PV panels. As shown in Figure F2H, the ESS was in normal working status. For example, the total voltage and maximum minimum cell voltages were in the normal range. As shown in Figure L, our normal energy consumption is about 125 watt. This energy is used for the working light. If the weather is too hot, the HVAC will be turned on, and the energy consumption will up to 800 watt. Alert messages are shown on the right side of the monitored dashboard. If there is something wrong, the system's current status will change from OK to alert, or other hint messages. The recent state changes are also given for users to track the system status. For example, all system current states show OK, indicating that the system worked in a good condition as shown in Figure O. While there was a signal loss event at 1:48, no data shows in Figure P. This example also demonstrates the importance of the event log. The state change history will tell us something special or abnormal even though we are not on site. In this case, at 1:48, we slept at home, and we were not in the company. The EMSW also provides a brief statistical report on the input and output energies. In the basic information, the energy generated by PV panels today, this week, this month, this year, and all time, are shown in figures A, 2, E, respectively. The energy consumption by loads today, this week, this month, this year, and all time, are shown in figures F, 2, J, respectively. This information gives users a brief understanding of the input and output energies. In the statistic report, the input and output energies today, this week, this month, and this year are given. From the hourly energy today, the report reflects the facts that the solar energy is generated during the day, no solar energy is generated at night, as shown in Figure K, and the energy consumption is larger during the working time as shown in Figure P, and the energy consumption is almost constant outside the working time as shown in Figure P. The weekly, monthly, and annual reports will reflect the seasonal fluctuation of solar energy, the feature of renewable energy, the seasonal usage of HVAC, as well as the sudden reduction in holidays and weekends. In the half hour, we have talked about the basics of Li-ion battery cells as well as engineering integrations, including battery management systems and energy management systems. Since the time is not sufficient, the rest sections will be presented in the next workshop. In the coming period of time, we will see the masterpiece of SDP, the off-grid solar energy storage system in Payun Lodge in Mount Jade, Taiwan. Mount Jade, also known as Mount Jade, Jade Mountain, or Yushan, Yushan in Taiwanese, is the highest mountain in Taiwan at 3,952 meters, 12,966 feet, above sea level, giving Taiwan the fourth highest maximum elevation of the island in the world. It's also the highest point in the Western Pacific region. Over 50,000 climbers around the world come every year. Conquering Mount Jade has been one of the most fascinating and difficult challenges for mountain hikers at home and abroad. Peiyun Lodge, located at 3,402 meters on the trail to the main peak of Mount Jade, is the important overnight boarding base for hikers planning to reach the summit of Mount Jade since 1943. Here you can see the sea of clouds, sunrise, sunset, night view, Milky Way galaxy, stars, and other special scenery. It was redesigned and rebuilt with modern facilities and then reopened in 2013. The new lodge is much larger and now provides more comfortable bedding, hot meals, as well as search and rescue services. Now, the lodge serves over 30,000 people every year. In the past half-century, the electricity is provided by the diesel generator with lead-acid batteries, which are high carbon emission and high pollution. In order to preserve the ecology of Mount Jade, the old system must be replaced. Eventually, the off-grid solar energy storage system is chosen from many options, such as building dozens of miles of power lines from a city power plant. The solar energy storage system is built on July 4, 2016. The electricity is purely generated by solar panels and can be saved in the energy storage system. Hence, the entire system guarantees green, zero carbon emission, eco-friendly, and sufficient energy. The rest of the electricity can be preserved in the energy storage system, constructed by lithium iron phosphate batteries of 72 kilowatt-hours capacity. If solar energy is not available, the system can provide electric power for about 1 week. Now, the solar energy storage system not only provides electricity for daily usage, but also gives a stable power supply for the automated external defibrillator, AED, medical oxygen generators for sudden mountain sickness, other basic medical equipment, as well as ambulance communications. Here a video will show how SDP moves the equipment up the Mount Jade and builds the off-grid solar energy storage system in Peiyun Lodge.